WhatsApp linkage for those who already registered for this webinar. For those who don't receive that schedule, the brief program schedule as follows.
For the kind notice of audience here, session 1 will start on 10:30 a.m. After that, lunch break, and that is followed by session 2 on 2 p.m. Session 1 don't have any feedback linkage. Feedback linkage will be provided at the end of the session 2 only. Those who wrote feedback alone will receive the participatory certificates. Kindly please note, those who wrote the feedback alone will receive the participatory certificates. Your active participation is important throughout the session. Right now, I want everyone to mute their microphones to avoid background noises that may distract you from disturbing the webinar. And before we get started, I would like to remind that if you have any questions during the presentation, you can kindly click the raise hand button, which is located on the lower part of the Google Meet. We will bring them up during the presentation. I hope you all will utilize them. Thank you.
First of all, I would like to invite a great supporter and renowned lecturer, Dr. Jenna, the Assistant Professor, Department of Physics, for welcome address. I invite you, ma'am.
Good morning to every one of you. It is indeed a matter of great honor for me to welcome all of you today for the National Seminar on Crystallization Techniques and Conjugated Polymers organized by PG and Research Department of Physics. First, I extend my warm welcome to the distinguished personalities, Dr. R. Ramesh Babu, Associate Professor, Department of Physics, Bharathidasan University, Tiruchirappalli. Next, I welcome Dr. T.S. Shabi, Scientist, CSIR, the Advanced Materials and Processes Research Institute, Bhopal, who are about to share their knowledge and experience with us. It's my pleasure to welcome our principal, Dr. G. Anlet, who is always supportive in conducting various webinars. And at the moment, I welcome our head of the department, Dr. S.L. Rayar, who took the initiative in conducting such a webinar. It's my pleasure to welcome the convener, Dr. T. Shajni Rose, and other staff members of our institution for their contribution is to be much appreciated. I also welcome the participants from all over India, the eminent personalities, professors of various institutions for participating in this webinar. I hope you all find the seminar highly fruitful and beneficial. Once again, I welcome all those participants present here. Thank you.
Thank you, ma'am. Thank you for your welcome address. A leader is one who knows the way, goes the way, and shows the way. Next, I would like to invite a dynamic personality, Dr. G. Anlet, the principal of our college, who inspires, motivates us, and guides us in a right way with her great leadership and inaugural address. I invite you, ma'am.
Thank you. Very good morning I'm very happy to be the part of this webinar conducted by PG and Research Department of Physics. This is a proud moment of Physics Department for organizing this two important session. I take this opportunity to congratulate Dr. Shajina Rose, convener, and other faculty members for organizing this program. I would like to thank Dr. Shabi, Dr. Ramesh for their acceptance to share their ideas. Research in physics generates fundamental knowledge needed for the future advanced research. It will continue to drive the economic engine of the world. Research in physics which extend and enhance our understanding of other disciplines such as the earth, environmental, astrophysics, and cosmology. Research in physics improves the quality of life, providing the basic understanding necessary for developing new instrumentation techniques for medical applications such as ultrasonic imaging and laser surgery. Dear all, I have to add one more thing. Among the nearby institution in our district, our institution only have FTR, UB, TG research facilities. Here, research scholars try to do multidisciplinary and interdisciplinary research, make your research more fruitful for the society. Whenever you get a chance to discuss with the experts like this platform, please raise your doubts and get clarity on your ideas. I wish you all the best to all the participants. Thank you all.
Thank you, ma'am, to give us the opening remarks for this program. Now, with much honor, I request Dr. S.L. Raya, the eminent personality and an excellent teacher, Associate Professor and HOD of Physics, to introduce the chief guest. Sir, please.
Thank you. Thank you for calling to introduce Dr. Ramesh Babu. It is a beautiful opportunity bestowed upon me to introduce such a great personality to all the eminent personalities who have gathered here. So he's a well-known person. Even then also, it is my duty to introduce him a little bit, his achievements in the field. Therefore, this will be very useful to you, I hope. With a small slide share here also. I am sharing this about the resource person, Dr. Ramesh Babu. He is an associate professor in the Bharadasan University, and he is leading the crystal growth and thin film laboratory in the Department of Physics, Bharadasan University. This he had around 20 years of teaching and research experience in Bharadasan University. If I could spell out his research activities, he had produced 13 PhD holders. 3 of them have been as the co-guide, 10 he had guided, and at present 3 more are doing their research studies. If we could recollect the papers published in international indexed journals, it comes to be 178. Only few had been published in the national papers. Rest of them would have been in the international papers. And he had presented 117 in the reputed conferences. And he had organized 6 conferences and seminars in Bharadasan University. And he had given around 105 invited talk in the conferences and seminars. We can put stars or asterisks in all the points because it is not an end. It is continuously going on. Coming back to the completed research projects, he had extracted around 1 crore and 29 lakhs from various funding agencies of the nation, from DST or UGC or SERB, like that. From all the funding agencies, he had extracted this amount for his research studies. At present, 2 projects are going on. One is under SERB for 35 lakhs. Another one is the MHRD RUSA project coming to be 16 lakhs. In all the most of the projects, he is the principal investigator. You can see how he is spending his time to write the project and extracting the money from the government for the welfare of the scientific society. And if you could see the citations under Google Scholar, the citation comes to be 3,509. And the H index is 34 and the I-10 index is 93. Here also we can put the asterisks because it is going on. And this was his achievement that we can see from the research studies. If we could recollect about his expertise, he is very good in the Bridgman methods to grow organic and inorganic crystals. And he is a very good expert in Sikorsky method while he was doing his MPhil studies under Professor K. Ramamurthy in Baradas University. He himself had devised that apparatus, Sikorsky apparatus, and he had grown that inorganic single crystals and so on. Such an eminent personality, hard-working personality is there amidst us. And he is also doing research in low temperature solution growth, thin film deposition, transparent conducting oxides, metal organic, nanomaterials and nanocrystals, organic polymer solar cells. And he had also written one book, Palliyil Padika Malar poem in Tamil. He's a very great scholar of Tamil. He used to write poems also. I had a chat with him. He used to write down all these things in a beautiful language. Palliyil Padika Malar poem in Tamil, it comes to be 201 pages, which was written along with Dr. Gopalakrishnan, his mentor, and Professor Ramasamy, the great Vice Chancellor of Alagappa University. And with them, he had written that book also, which will be very useful for the students. And he's in the professional contribution, he's a life member in Indian Association for Crystal Growth and Japan Society for Applied Physics. Apart from that, he is an advisory committee member in Science and Technology Journal of Elsewhere Publications and so on. Because of this, you can see the various awards he had received. Tamil Nadu Young Scientist Award in 2018, Fellow of Academic Sciences in 2018, Postdoctoral Fellowship in Aichi Institute of Technology, Japan. He was there for 1 year in Japan and he did his research there. Then he came here and he was awarded the Young Scientist Fellowship by DST Fast Track Government of India, Tamil Nadu Young Scientist Fellowship Award in 2008, Senior Research Fellow, Government of India. So these are the awards and fellowships that he had received. Surely he will have so many feathers in his cap in the later years also. And he himself had developed the following facilities in the Bharatdasan University. Low temperature solution growth for unidirectional solution growth setup, a vertical dynamic gradient freeze unit Bridgman setup for organic crystals, Sikorsky unit for inorganic crystals, top-seeded solution growth setup, spray pyrolysis setup, spin coating unit, and for characterization, he made the facilities for Hall arrangement to measure the dielectric constants and so on. So these are the facilities that he had created in his university. You see the hard work, the commitment, the time that he is spending for the scientific community and for the younger generation. Such a great personality is amongst us, and we are privileged to have him here. Moreover, here he used to give the invited talk to the people in and around Tamil Nadu and throughout India. Such an eminent personality is here. We can listen to him and we can benefit from out of him. I welcome such a great personality. Welcome, Dr. Ramesh sir. Now, with this few introduction, let me give the mic to the host team. Thank you.
Thank you, sir. Thank you for your elaborate introduction about me. You are my one of the mentors as well as the well-wisher. Okay, so thank you so much, sir, for your nice introduction.
Thank you.
So a very good morning to all of you. First of all, I would like to thank the administrator as well as the administrative officer and principal of this great college, St. Jude's College, and then head of the Department of Physics, Professor S.L. Rayar, and convener of this conference, Dr. Sajini Rose, and all the faculty members of this physics department for giving this opportunity to share some of my knowledge on crystal growth in this national webinar on crystallization techniques and conjugated polymers. In this lecture, so now I would like to share my screen, sir. So my window is visible, sir. Hello, sir.
Yes, visible, but not in the slide share mode.
Now,
Yes.
okay, sir.
Now it's okay.
Yeah. Thank you, sir. Thank you. Actually, in this lecture, I'm going to give idea about how to use a simple technique to grow good quality and bulk single crystals for different applications. So here I'm going to discuss a very simple techniques to grow a bulk single crystals. I have chosen the unidirectional grow techniques to grow a bulk single crystals. First, I will discuss crystal growth by solution method. If time permit, I will also discuss that crystal growth by melt techniques also. This is my plan of lecture. For the beginners, first I will discuss that I will give some introduction to crystals and their applications. Then I will explain about that importance of unidirectional solution growth techniques. Then the crystal growth techniques which are available to grow bulk single crystals. In particular, solution and melt growth techniques will be discussed in this seminar. So my part, so I will discuss that the growth of bulk single crystals using solution as well as the melt growth techniques. Then the characterization techniques which we have carried out on the grown single crystals will be discussed. Finally, I'll conclude my lecture. Even though we are in the era of nanotechnology, for many specific applications, we need bulk single crystals. You see, we are using these single crystals in our day-to-day life. Without crystals, we cannot imagine today's advanced technologies. You see, in the ancient days, these crystals used as weapons. Different kind of weapons, so they developed using the this type of crystals in order to hunt the animals. So these are all the shapes of that crystals or knives. So using the crystals, they developed these type of weapons to hunt the animals. In the mid of the century, so even you see that in ancient days, crystals used as ornaments purpose, like a ruby, emerald, and then many other crystals, diamond, used as ornament purpose. So you see that In mid of the century, these crystals used to heal the wounds. So therefore, these crystals are called as the magical crystals. In order to heal the wounds, they used these type of crystals. Even now, you see that 30 type of crystals, so they are selling so for anchor management purposes. So now these crystals are available in markets. Then you see that in ancient days, the crystals used as amulets. So this is the single crystals. So used for in these amulets. So you see that these crystals used as for this purpose. Without knowing the scientific information on these crystals, in ancient days, these crystals used in very many purposes. Then, in the mid of the century, previous century, after the invention of this piezoelectric effect in quartz single crystals, most of the quartz single crystals they exhibit the piezoelectric effect. So then the piezoelectric crystals used in watches. So now we can, for the beginners, I would like to give some idea about what is piezoelectric effect. If we supply a force to the piezoelectric crystals, that can develop some electrical energy. This is also inverse also means so we can also produce the inverse piezoelectric effect by applying the electric field, so we can generate the mechanical vibration with this principle. So these quartz single crystals used in watches, you see, uh, when you take the backside of these watches, so we can find these piezoelectric crystals in the portion of this is the quartz crystals. These quartz crystals, so is kept inside that watches. So for the purpose of, you see that this is the quartz crystals taken and then shaped like a quartz element. So and then it makes like a quartz oscillators. So then it is taken in this quartz oscillators. Then this one is installed here in watches. Okay, so in order to run the watches, so these quartz crystals are very important one. Even though there are very many parts in the watches, like electronic components, stepping motors, and mechanical components, and other things, this quartz crystal is very important part in the watches. Okay, so this one is installed at this position. Okay, this is one. So quartz oscillators. Then the mid of the centuries, so after the invention of transistors, these semiconducting properties established. So these crystals used in semiconductor detectors. So then short devices like in a piezoelectric substrates. So in order to design the surface acoustic wave devices, these piezoelectric single crystals used. So this is the circuit diagram of these short devices. Then even in order to produce the new type of lasers using this type of single crystals, so the second harmonic generators developed using the very many single crystals. You see that, so we can use the red color pointer, okay, for presentations. We can also change this red color into a green color by using the different type of lasers that has the properties of second harmonic generation properties. This is the one of the simple example. We can say the applications of single crystals. Okay, second harmonic generation properties of single crystals. Okay, Using this type of single crystals, we can produce new type of wavelength with lasers with a different wavelength. Then you see nowadays these single crystals are used in for developing the solar cells. The solar cells, even though you see we are in the preparation of fourth generation of solar cells, like there are four generation of solar cells developed by different researchers. The first generations is based on the silicon single crystals. The second generation is based on the thin film based one. The third generation, that is the organic polymers, nanomaterials, dye-sensitized solar cells. Now fourth generation solar cells is based on the perovskite based type of materials. Even though we are in the preparation of fourth generation of solar cells, the entire solar cell industry occupied by only one material, that is called silicon single crystals. Okay, so you see that on the silicon single crystals, these circuits are made. So the silicon single crystals grown by the techniques called, that is the Jokralski technique. You see that this is the length of the single crystals, and then diameter, it may be the 40 centimeter diameter single crystals. Then these grown single crystals cut and polished like a wafer one. Okay. So nowadays, these single crystal based solar cells used in very many places in order to harvest the electricity using the sunlights. So now, then this type of single crystals are also used in very many applications in medicine. So for surgery purpose, so even so for very many applications, eye surgery, and then for healing some other wounds. So many other applications. So they used this type of single crystal based laser materials. So for laser cutting and cutting purpose, so these single crystal based laser materials are used. So even though we can derive n number of information from satellite, in order to run the satellite, it needs a power that the solar panels so developed only by the single crystal based materials. Okay, so far I have given some applications of these single crystals. So now we can go for discussing that what is single crystals. This is the photographs of these crystals. This is nature grown single crystal. All the three photographs taken from the nature, you see that this is the snow single crystals, not grown synthetically. This is the nature grown crystals. So this is the dendritic form of snow crystals. The second one is the quartz single crystals. This is the NaCl. So we are using the in our day-to-day life, the NaCl crystals. The synthetically grown single crystals like a potassium dihydrogen orthophosphate. This is the cut and polished piece. This is lithium borate crystals. Then this one is the ruby crystals. This is grown by the Jokralski technique. This one is the vapor grown single physical vapor techniques grown single crystals. We can usually this type of single crystals we can classify like so what is the definition for crystals? Crystal is a regular periodic arrangement of atoms in three dimensions. As we all know, the matter exists in the four form. Depending upon the atomic arrangements, we can classify these states like solid, liquid, gaseous, as well as the plasma. Okay, these crystals comes under the category of solid material, solid category, solid state. Further, this solid state is categorized by two. One is crystalline one, and another one is the amorphous materials, non-crystalline and crystalline materials. Crystalline means the regular periodic, the arrangement of atoms in a periodic manner in 3 dimensions. Suppose that maintains the periodicity in a long range order. So that is called a single crystalline materials, or otherwise that maintains the periodicity is in short range order, that is called polycrystalline materials. This polycrystalline, again, that also has some grain boundaries. Okay, this is the amorphous material, crystalline and amorphous. The amorphous is nothing but the non-crystalline material. This type of materials not maintain the periodicity, so and then lacks of symmetry. Symmetry means the regular periodicity of atoms, ions, or molecules. So here, amorphous materials, no periodicity maintained, as well as the lacks of symmetry. Okay, so most of the device applications, we need bulk single crystals, as well as the most of the device applications, the single crystals used. Why do we need single crystals? You see that this type of polycrystalline and amorphous material that contains the grain boundaries. These grain boundaries acts like a defect centers. Many physical properties of solids are observed by the effects of grain boundaries. So therefore, the properties of single crystals decided by the internal symmetry of that materials. So internal symmetry of that material. So therefore, when compared to polycrystalline as well as the amorphous material, this single crystals has somewhat better internal symmetry. So therefore, so for many applications, the single crystals used. So for example, so we can say piezoelectric devices as well as the ferroelectric devices, nonlinear optical devices, semiconductor devices developed using this type of single crystal type of materials. So then the classification materials, uh, depending upon the bonding properties or binding properties, we can classify this type of materials, crystals, like ionic crystal, metallic crystals, covalent, and molecular crystals. So likewise, so depending upon the property exhibited by that materials, like suppose a material that has the properties of semiconducting properties, we can use that material for semiconductor device applications. Likewise, suppose a material that exhibits the piezoelectric properties, we can use to develop the piezoelectric devices using that material. So therefore, that crystal is called as a piezoelectric crystal. Likewise, so we can develop materials with different properties like a ferroelectric crystal, electro-optic crystal, superconducting crystal, non-linear optical crystals, biological crystals, and magnetic crystals. Okay. So in ancient days, these type of single crystals like a diamond, quartz, ruby, and other things, we can derive or get from our mother earth. When you dig our mother earth, we can find even diamond. So, so that is the diamond is one form of carbon. So this carbon, so get into the earth. So after the 100 years, so the crystallization forms a different form of carbon that is called a diamond one. So in ancient days, so we can get this type of diamond and ruby and other quartz crystals from our mother earth. After the invention of transistors based on the silicon single crystals, so scientists, they need more number of silicon materials to develop or to develop the electronic industry as well as the electronic gadgets based on the transistors. So for that, you see that so the natural crystals like a diamonds, ruby, quartz, So that time, ancient days, we can derive from our Mother Earth. But so after the development of this type of transistors, so they need more number of single crystals. Therefore, so that is the increasing applications of the crystals in the mid of the previous century. Then the lack of crystals in natures. So then many scientists, they developed new techniques to synthetically grow the single crystals for different applications. Initially, you see that Jokralski in 1918, he developed a technique called Jokralski technique from melt one. So he developed silicon single crystals to grow as a bulk one for transistor applications. So very many scientists involved to develop different techniques to grow a single crystals for different applications. Basically, we can classify this crystal growth technique like a solution growth techniques, melt growth, as well as the vapor growth techniques. That these three techniques categorized by the means of the phase transformations occur during the crystal growth. You see, any crystal growth, it needs a careful control of phase change. Phase change means phase transformations. From liquid to solid transformation, that is the phase transformation, or otherwise vapor to solid transformations, that is also a phase transformation, or otherwise the solid to solid transformations. Based on this phase transformation only, these crystal growth techniques categorized like a solution growth, melt growth, as well as the vapor growth techniques. Here you see that suppose growth from solution or melt. So here we can find that is the liquid to solid transformation or phase transformations involving. That is the process involving liquid to solid phase transformations. So we can categorize this type of transformations like a solution technique and then melt technique. Then one more technique, that is the solid transformations. This is also a one type of phase transformations. This is called as a solid growth. This is the rare technique to use to grow a crystals. Then the vapor to solid growth, that is the process involving vapor to solid phase transformations. Based on this one, so we can categorize solution growth techniques, melt growth techniques, and then vapor growth techniques. Okay. Under these crystal growth techniques, there are three different major techniques available: vapor techniques, solution techniques, melt growth techniques. Under these three techniques, there are n number of investigators or researchers involved to develop new technique with the different modifications in the instrument. So they develop the crystal growth technique like a chemical vapor transport as well as the physical vapor transport. These two methods comes under the category of vapor growth techniques to grow a single crystals. Even by depositions, we can prepare the thin films, chemical vapor deposition and physical vapor deposition. Under the solution growth techniques, there are two major techniques available. One is low temperature solution growth and another one is the high temperature solution growth technique. Under this low temperature solution growth techniques, slow cooling and slow evaporation and temperature gradient techniques are also available to grow crystals. Under this high temperature, you see that the hydrothermal growth as well as the flux growth comes under the high temperature solution growth techniques. These melt growth techniques, so whatever the crystals we used in previous century, and then what are the crystals we are using in the present days, as well as we are going to use for different application in future. These crystals only grown, most of the crystals grown only by this melt growth techniques. because almost 85% of the single crystals grown by these melt grow techniques used in device applications. So, so I have listed so very few techniques under this melt grow techniques, like a Bridgman. This techniques developed by the Bridgman and Stockbarker. This is called a Bridgman technique, as well as the Jokralski technique. Scientist Jokralski developed this Jokralski technique. Then the Verneuil technique. There are zone melting and n number of melt grow techniques available. So even though there are n number of methods available under these melt grow techniques, Bridgman and Jokralski contribute lot to grow a bulk single crystals for very many device applications, even for solar cell applications, for optical applications, for that is the second harmonic generation, and very many applications. So this Bridgman and Jokralski grown single crystals used. Yes. You can choose any type of single crystal grow techniques to grow a single crystals. The following steps, so you have to take care or follow these important steps involves in the any types of crystal growth. One is, first one is the, you have to take care about the achievement or attainment of supersaturation. Before the achieving the bulk single crystals, we need to follow step-by-step process. The first step, we need to achieve or attain the supersaturation. It may be a solution or melt, okay, or vapor. So this is the first step. We need to achieve or attain the supersaturation. Then only possible the nucleation in the solution or melt or vapor. Okay, the formation of nuclei so happen or occur only after achieving the supersaturation in the solution. So after attaining that nucleation in the solutions, that nucleation grow as a bulk clusters and then bulk size like a critical nucleus. After that only we can obtain the bulk single crystals. Okay, this is the step-by-step process. So first we need to achieve the supersaturation, then only after achieving supersaturation only there is a possibility of obtain that nucleation in the solution. After attaining that nucleations, so that grow as a bulk one. So we can get that bulk single crystals from the solution or melt or vapor growth techniques. These are all the very important steps to grow a single crystals by any crystal growth techniques. Now, I would like to enter into the, with these small basics. So I would like to enter into the low temperature solution growth techniques. So here, before going to discuss the low temperature solution growth techniques, so I would like to give some of the basics involved in the solution growth technique. The first one, what is solution? Solution is nothing but the homogeneous mixture of solute as well as the solvent. We know that, so every day, so in our life, we are preparing some type of solutions. For example, you take a coffee powder and then milk as a solvent. Okay, so if you need a high concentration coffee, you mix a coffee powder with a highly concentrated one. So we can prepare the coffee. So using the homogeneous mixture of solute as well as the solvent. Okay, coffee powder here the solute, as solvent is the milk. Okay, so if you need a light concentrations, you can add the solute in a very minimum quantity, so we can end up with the solutions. So this type, we every day we are preparing some type of solution. That is the definition in the solution growth. The homogeneous mixture of solute and solvent that gives the solution. solubility and the saturation, these solubility as well as the saturation is the same meaning, that gives the same meaning. The saturation of the solution or solubility of the solution, how we can define means, you see, an amount of solute dissolve in a particular amount of solvent at a given temperature. Here, each word is very, very important. So, in a particular amount of solvent, why? So, I am pressing this word means, so you can take 100 ml of solvent, so you can dissolve some amount of solute. So, we can, for example, 100 ml of solvent, so we can dissolve 20 grams. So, just you can take a 200 ml of solvent, so we can dissolve more amount of solvent. So therefore, in definition, an amount of solute dissolve in a particular amount of solvent. It may be 50 ml or 100 ml or 200 ml. So there we have to identify how much of amount dissolved. That is the amount of solute dissolved. Okay. So then next point, at a given temperature. Yes, this is also here also this temperature. When you change the temperature, so for example, when you prepare a solution at room temperatures, so we can dissolve some 20 grams in 100 ml. Just you can increase the solution temperature of the solution. So to room temperature to 50 degree, we can add more number of solute. So therefore, so here at a given temperature is a important word. So so you should read this definition carefully, because so this each and every word in the definitions is very, very important in solubility definitions. An amount of solute dissolve in a particular amount of solvent at a given temperature. I can give some very good example. You take a water solvent 100 ml. Okay, so at room temperature is a 30 degree centigrade. Room temperature is 30 degrees centigrade. So room temperature is 30 degrees centigrade. 100 ml solvent, so 100 ml. Okay, so just you can take 100 ml solvent. So then room temperature is 30 degrees centigrade. So now you can dissolve some material. You can dissolve so up to 20 grams. So this material is dissolved in 100 ml. Okay, so that is the solubility of that material at 100 ml solution at 30 degrees centigrade. Now, just you can increase the temperature from 30 to 40. We can add more number of solute. We can add more number of solute. So by the way, so we can measure the solubility of that material with a different temperature, as well as you can increase the solvent amount from 100 ml to 200 ml. We can also increase the solubility range, that is from 20 gram to another amount we can dissolve in that solute, because we increase the solution of the solvent amount. Okay, so here this is the definitions, the first one. The next the concentration available in that solution is called as the equilibrium concentrations. Suppose the concentration of saturated solution is called equilibrium concentrations. Okay, so our aim to grow a single crystals. So for that, first we should achieve the supersaturation in the solution. We have saturated solution, but how we can achieve the supersaturation? I have the definition for super solubility or super saturation of solution. Suppose the solution concentration is above the equilibrium concentrations, that is called a super saturations. Suppose the solution concentration is equilibrium concentration, means that is called a solubility of the solution. The solution concentration is above equilibrium concentration, means that is called super solubility or super saturation of the solution. Yes, here achieving the super solubility or super saturation is not a easy job in this low temperature solution growth. So that is the techniques we have to learn in this low temperature solution growth techniques. Okay, so the next one, that is the nucleation. Nucleation is nothing but the uh, group of atoms or molecules or ions formed in the supersaturated solution called as, so the initial stage of nuclei is called as embryo. So then it grow as a bulk one, so it form a clusters, then it reaches the critical nucleus, then it grow as a bulk one, bulk crystals. From the embryo to bulk single crystals, step by step process we can attain in the solutions. These are all some of the basics involved in the solution growth techniques. First, we need to understand what is the definition for solution. The second one, what is the definition for solubility or saturation. The third one, what is the definition for super solubility and super saturation. The fourth one, that is the nucleation. Okay, with these small basics, so I can enter into the low temperature solution growth techniques. So low temperature means, don't think this is the below the room temperature. Actually, this temperature range is from room temperature to up to 100 degrees centigrade or 80 degrees centigrade. Whether when we perform a experiment from room temperature to up to 100 degrees centigrade, this is called a low temperature range in the solution growth techniques. Requirements, so for this technique we need a solute with high purity. You know that there are n number of chemical companies, they are selling these chemicals with a different purity. So we can purchase the same chemicals from our local chemical agent, as well as the Sigma Aldrich, as well as some other Alpha Icer and some other foreign companies. So from the foreign company, the same material we can purchase with the high purity. So they can mention that is the 99.99 percentage, 99 purity. Okay. What is the purity? Purity means this crystallization itself is called as the purification process. Yes. So suppose you can purchase the same material from our local company, 500, they will give 500 grams of KDP. So the with the amount of rupees 500 rupees 500 only. Whereas the same one, so you can purchase from the foreign chemical agent. So they'll give that 5 grams, 5 grams, 5,000 rupees. The cost of 5,000 rupees. Why? Because they purified these materials. They achieved the high purity materials. So they are selling the 99.99 percentage. We can improve the purity to the 8N purity or 9N purity or 3N purity, different kind of purity levels available. Okay, with respect to this purity, so we have to improve the purity of that materials. So therefore the cost of the material also increase. So when you increase the purity of that materials, so for device application, why I am pressing this word means, when you use a low quality materials, so finally we can end up with the low quality crystals. So that gives the that also affect the quality of the devices what we are going to develop using that type of crystals. That is the idea. So therefore, try to purchase the high quality or high purity chemicals for your research, or otherwise you can purchase these low quality chemicals and you do some recrystallization process by means of solution technique or melt grow techniques. You can improve the purity of your materials before going to grow as a bulk single crystals. Okay, then we have to choose the proper solvent to grow a bulk single crystals. For example, you see, uh, suppose you take a X is a material name, X is a material name. So you dissolve that X into the 100 ml of solvent. So 100 ml of solvent, 100 ml of solvent, X dissolve 100 grams. 100 grams of X you dissolve there. Okay, so that is called as a high solubility material. This type of high solubility lead to multinucleations. Means multinucleation means, so instead of obtaining the single nucleations or few nucleations, we obtain that more number of nucleations, so that usually that multinucleations, so when we obtain the multinucleation in the solutions, so our aim to grow a bulk single crystals, so these multinucleations leads to small single crystals only in the solution growth techniques. So therefore we need to achieve the single nucleations or very few nucleations. We need to control the nucleations, so using these techniques. Therefore, suppose a material or solvent highly dissolved one, so we need first, so we need to find another solvent for the growth. For example, the solubility, suppose is you take a low solubility solvent, means 100 ml of solvent, you are dissolving only 1 gram, means finally we can end up with the 1 gram crystals. So that also take more time to nucleate. So therefore low solubility require more time for nucleation. High solubility that lead to multinucleation. Low solubility require more time for nucleations. So therefore we need to choose moderately dissolved solute, that solvent with moderately dissolve the solute. Means suppose 100 ml of solvent, when you dissolve 20 grams or 25 grams, this is called a moderately dissolved solute. Or even for 50 grams or 60 grams, also a moderately dissolved solution. So therefore, so you can choose a proper solvent, okay, with moderately dissolve the solute. So then the solubility of the solute in solvent at different temperatures. As I have discussed in the previous slides, we can also collect the solubility data or saturation data at a different temperature with a different solvent. That gives the idea about how much of amount we can dissolve in a particular amount of solvent at a particular temperature. So this idea we can get that solubility when we collect a solubility data using the solvent as well as the our solute with the different temperatures, when you dissolve with the different temperatures. This is mostly we can study from the temperature concentration diagram, so of the solute. So I can discuss that temperature concentration diagram. This is the standard temperature concentration diagram discussed by the scientist Mayer for low temperature solution growth technique. Here you see that this is the simple method to know the two different solution growth techniques. By means of learning this Mayer solubility diagrams, we can also learn two different solution grow techniques from which. So here you see that. So I have given in the x-axis, I have given the temperature. In the y-axis, I have given that concentration. Okay, so how much of the solute dissolved in the solvent. So that concentration I have given in the y-axis. So now I am going to take 100 ml of solute, 100 ml of solvent, 100 ml of solvent. So all the experiment I have performed the same amount of solvent I have taken, that is the 100 ml of solvent at 30 degrees centigrade. This is the 30 degrees centigrade. This much of concentration I have dissolved. So then I pointed out here. So then 40 degrees centigrade, this is the amount of solute I dissolved. At 50 degrees centigrade, this is the amount of solute I dissolved. So this is the 60 degrees centigrade. This is the amount of solute I dissolved. Okay. So now you connect all these points, So by connecting all these points, we can form this is called a solubility curve. So solubility curve. This solubility curve we can learn from when you prepare a solution at a different temperatures, so at a particular amount of salt. Okay, so this is the solubility curve. Sir? Hello, sir.
No, some interference from someone else. JNT.
Yes, sir. So this is the solubility curve. Our aim not to prepare a solubility curve. Our aim to prepare a super solubility curve. So therefore, in order to achieve the super solubility, so now we have to prepare that super solubility solution by means of two ways we can follow. First one, you see that. First one, you can follow. I can choose this temperature, that is the 50 degrees centigrade, dissolved this much of amount, that gives the solubility data, from which this solubility data, we need to achieve the super solubility data. So the first way, that is A to B. A to B means at a constant temperature, maintain temperature at a constant. Okay, so now we have to vary the concentrations. So in order to achieve the super solubility curve, or otherwise, that is the to reach the B positions. Okay, so at a constant temperature, 50 degrees centigrade, we need to change the concentration of the solution. This is the one way, first way. So by means of changing the concentrations, we can achieve the super solubility. So how we can achieve that super saturation? So any one student can answer? Yes. So we can achieve from solubility to super solubility, from achieving A to B. So you see that by means of slow evaporation of solvent. We can achieve easily from solubility to super solubility. The definition for solubility is equilibrium. The concentration exists in the solubility solution, that is called as a equilibrium concentrations. Whereas in the super solubility, that is called above equilibrium concentration, the concentration is more than equilibrium concentrations. In order to prepare the solution with more than equilibrium concentrations, we need to follow, that is the slow evaporation technique. At a constant temperature, just you can evaporate the solvent. So there we can achieve the more than equilibrium concentrations. For example, you take 100 ml of solvent, 100 ml of solvent, okay, at 50 degrees centigrade, you dissolve 30 grams, okay, 100 ml of solvent, 50 degrees centigrade, you dissolve 30 grams, 30 grams. Okay, so after applying that slow evaporation, or by means of slow evaporations, you can evaporate the solvent now. From 100 ml to that reaches after 3 days, that 100 ml of solvent reduces to 80 ml. But the concentrations what we have dissolved 30 grams, the same 30 gram exists in that solutions. You see, previously you prepared in 100 ml 30 grams at 50 degrees centigrade. Now, after evaporating the solvent at constant temperatures, now you achieved at 80 ml, 80 ml solvent. So at 50 degrees centigrade, the same amount of 30 grams exists. So this is called, so we achieved more than equilibrium concentrations. So this is called a super solubility of the solutions. Okay, by means of evaporating the solvent or slow evaporation method, so we can achieve super solubility of the solvent. So the same type you can do the experiment for different at different temperatures. So when you connect all these points, so we can get this type of curve that is called super solubility curve. Okay, this is the one of the low temperature solution growth techniques, that is the slow solvent evaporation technique. Okay, so need to achieve the saturation to super saturation of the solutions. Yes, after achieving the super saturations, then the nucleation forms in the solutions, then we can grow a bulk single crystal. This is the one technique we can learn from the Mayer solubility diagrams. The another technique, that is the next technique. You see, there are another way to achieve the super solubility. That is, you see that the same 50 degree centigrade I have chosen now. So now I would like to follow the position from A to C. Now the way is different. So the previously I follow A to B. So now the way is A to C. So the how we can achieve A to C means at a constant concentration. At a constant concentrations, don't vary the concentration of the solution. Just you can vary the temperature from higher temperature to lower temperature. For example, the initial temperature T2, the final temperature is T2, T1. This is called the initial temperature, that solubility. So we achieved at this point, A point. So in order to achieve the nucleation point, this is the C point, is a nucleation point. The temperature is reduced from T1 to T2 at constant concentrations. At constant concentrations. This is the constant concentration. Okay, this is called a slow cooling technique. Here also we achieved the solution concentration more than equilibrium concentration. Yes, you see that initially I prepared solubility data at 50 degrees centigrade, we dissolved 30 grams. We dissolved 30 grams only. So now you reduce the temperatures. We reduce the temperature from 50 to 40 slowly. Okay. So now you see the 30 grams, the same 30 grams exist in the solutions. but the temperatures what you prepared in the saturated solution at 50 degrees centigrade. So whereas here that is the 40 degrees centigrade. Okay, so if in 50 degrees centigrade, so you dissolved in 30 grams, the same amount so exists in the 40 degrees centigrade also. So this is called we achieved more than equilibrium concentrations. So this is we can achieve by means of slow cooling of solution, slow cooling of solution at constant concentrations, at constant concentrations. This is the this is also one of the methods in low temperature solution growth technique called as slow cooling technique. Slow cooling technique. Yes. So by means of slow cooling technique, also we can achieve the super solubility. Okay. Yes, this type of Mayer's solubility diagram also gives very many informations. Like you see that above the supersaturation line, like this is the supersaturation line. So we can form by following the way A to B, the first super solubility we can form, or otherwise you can follow the A to C. That is also one of the methods to achieve the solubility to super solubility. Two methods available. Above the super solubility, please wait, sir. Above the super solubility, you see that there is a region called as labile zone, that is also called as unstable zone. Unstable zone. Yes. After achieving the super solubility above this one, so we that leads to multinucleation or spurious nucleations. That is not useful to grow a bulk single crystals. So therefore, this is called as unstable zone. Or otherwise, so below this solubility zone, there is a zone called as the stable zone, that is also called as the undersaturated zone. Undersaturated zone means undersaturated zone is called as stable zone. No means of nucleation occur in this solution, because in order to achieve the nucleations, we need to achieve the super solubility. So therefore, in order to achieve the solubility, it needs more amount of solute. Therefore, it is called as the undersaturated solution. So undersaturated solution. In between this solubility as well as the super solubility, we have the zone called as the metastable zone. Yes, this is the metastable zone. In this metastable zone, we can grow very good quality single crystals. When you optimize the temperature between the solubility as well as the super solubility of the materials, so we can get the metastable zone with. For example, different kind of materials that has the different kind of metastable zone with. So we need to initially, before going to grow a single crystals by solution technique, using this solubility data, we need to understand what is the region that is the metastable zone region or metastable zone width. For example, some materials, it may be a 5 degrees centigrade, or some material, it may be a 2 degrees centigrade, some material, it may be a 10 degrees centigrade. We need to understand that temperatures, then you can start your crystal growth. So any one of the temperature at this metastable zone, so then you can start to grow a good quality single crystal at this zone. So mostly in this solution grow techniques, very many single crystals grown by worldwide, even bulk single crystals for fusion experiments. So grown by different researchers, even KDP single crystals grown by this simple solution techniques. So they used this metastable zone with zones to grow a bulk single crystals with less defects. Okay. Yes, in order to maintain the temperature constant, so we can use this constant temperature bath. So here you see that in constant temperature bath, we can place our solution in this position. So in order to maintain the constant temperature in the bath, we have two stirrers. So and then provide the heat. So heaters also provided. So then in order to observe the growth front, so we have the uh, illuminators, that is the bulbs type illuminators. So generally this type of constant temperature bath is used for maintain or control the temperatures environment. The limitation of these solution growth techniques, metals cannot be grown by this technique. Crystal growth takes more time when compared to melt growth techniques. Sometimes, so not all the cases, in some cases, the inclusion of solvent is possible. Means, I want to grow a single crystal of X. Sometimes using the solvent like a water, the single crystal grown by this water means water solvent means sometimes these water molecules may include into the X, that is the our material. So therefore, so we can end up with the X dot H2O or 2H2O hydrated materials. That is not useful for our purpose. So our aim to grow material like a X, so we end up with the X dot H2O or X dot 2H2O, like hydrated materials. So this is not all the cases in solution growth. Some cases, this type of solvent molecules are included during the crystal growth. Uh, Generally, in the amino acid type of single crystals growth, amino acid type of single crystal growth, microbial growth is unavoidable. Means during the crystallization of amino acid based materials, this amino acid is nothing but the body fluids. Okay, there are 20 plus amino acids available. So when you use this type of amino acid for our crystal growth purpose, so we know that these amino acids are highly viscous ones. It takes more time to grow as a to nucleate. So therefore, so the prolong so we have to wait for a long time to nucleate. So therefore, this it may be a 2 month time or 3 month time it will take. So for a long time, so sometimes in solutions there is a possibility of fungal formations or microbial formations in the solutions. So that is unavoidable during the amino acid based materials, during the growth of amino acid based materials. Yes, now only I would like to enter into our topic. With these basics, I'm going to enter into the unidirectional growth of single crystals. Yes. So you see that there are many advantages we can encounter when you use this type of unidirectional solution growth techniques. The first one, bulk single crystals with specific orientations is possible in this technique. So we know that the single crystals that has the peculiar properties, so like anisotropic properties. Anisotropic means directional dependent properties. The same crystals, for example, this is the morphology of the crystals grown. Okay, so this you see that this morphology, so it has the different crystal planes. Okay, different crystal planes or different facets. Okay, so when you measure any properties, we need to use any specific directions. Suppose you can measure any properties, for example, piezoelectric coefficient. in some directions, some specific directions. So when you measure the piezoelectric coefficient, so for the same crystals with the different directions, that gives different values. Okay, so we need to identify which direction gives the high efficient or high coefficient piezoelectric coefficient. So I have to choose that directions to grow as a bulk single crystals in this unidirectional technique. So why I have to choose that one only means that direction gives the very high piezoelectric coefficient, or that gives the very high second harmonic generations, or otherwise, so that it gives the very high properties, hardness properties. So likewise, we need to understand which direction gives the high coefficient. So we can use that direction to grow as a bulk single crystals by the method of unidirectional single crystals method. So for this is the conventionally grown single crystals. You see it has the different phases. So while growing a single crystal from conventional solution grow technique, like a slow evaporation and a slow cooling technique, we can end up with the crystals with a definite morphology like this. Okay, by means of Miller indices, we can represent the facets like a 100, 011, like a different names we can give that facets. Okay, so here, so we can choose any directions that gives the high coefficient. So for example, I can choose this direction to grow a single crystals. Now I have to cut and polish these directions to grow a bulk single crystals of this 011 directions. Okay, so because this directions only gives the high coefficient, so therefore other part are wasted here, because when you use a conventional grown single crystals, we need to identify the specific directions and cut and polish. We need to use that crystals in the device applications. Other part like this part, and then this part are wasted ones. So here we can avoid that also. So because we have chosen that specific directions, we grown as a bulk single crystals using this unidirectional technique. Almost entire quantity of the solute can be converted into the crystals. For example, in conventional solution grow techniques, suppose in order to grow a 10 gram of crystals, now we have to prepare a solution with 100 ml. We need to dissolve the 20 gram of solute. Okay, so that crystallizes like 10 gram of crystals we can harvest from conventional technique. So because other solutes are wasted in the solutions. Okay, so we can avoid that one, wasting the materials in the conventional solution grow technique. That also we can avoid here when we use a 100 ml of solution. There are 20 grams solute. Suppose when we take a 20 gram solute in a solution, all the 20 gram crystallizes in this unidirectional solution growth technique. That is the second advantage. Almost the entire quantity of the solute can be converted into the crystals. Then microbial growth is also avoided. We can also avoid this microbial growth. Then shaped crystal growth, any type of shapes we can grow using this unidirectional solution growth method. This is the reference. Our Indian scientists like Shankar Narayanan and Ramaswamy, they developed these techniques like a unidirectional solution growth technique, also called as the Shankar Narayanan Ramaswamy technique. So this is the simple setup which we have developed. Our inventors, they developed to grow a benzophenol single crystal. Very simple technique. Even MSc student can develop this technique in his laboratory. So you see that this is the water bath. This one is the water bath. Okay, so outer jacket is the water bath. So this one is the water bath. Okay, so even we can use the fish tank, so like a water bath. So you can close this fish tank using the thermocol sheet. So above this thermocol sheet, in order to place your crucible, this is the crucible or ampoule is the scientific name. So like a vessel, so the material has to take in that vessel, that is called a crucible or ampoule. So we have to place that ampoule or crucible inside that water bath. So we need to make a, okay, so arrangements in that thermocol sheet. So then you can place your crucible inside that uh, water bath. So before that, so first you have to place the seed crystals which you have prepared here. So this is the seed crystals. This is the cut and polished piece of the seed crystals. This is the directions which I want to grow as a bulk single crystals. For example, 0, 1, 1 directions. I want to grow as a bulk single crystals by this unidirectional method means. So I have to install that crystals. So or otherwise I have to place that crystals in this bottom. This is the seed crystals. This is the seed mounting pad. This is the seed mounting pad. So now whatever the directions you want to grow as a bulk single crystal, that has to see the solution, that has to see the solutions. Then you can pour the solutions already prepared, saturated solutions. You can pour from the top of the vessel, top of the vessels. So after the filling out that solutions, now, so suppose the seed crystals dissolved means we prepare the undersaturated solutions. Okay, so we need to once again you need to prepare the saturated solutions. Then you can pour the solutions inside this vessel. So now, in order to achieve the super saturations, so they use the ring heater in the top of the vessels. In the top of the vessel, they use the ring heater. They provide some temperature at the top of the vessels. So by means of evaporating the solvent at the top of the vessels, they achieve the they increase the concentration of the solute at the top of the vessels. Yes, gravity driven, by means of gravity driven solution concentrations, by means of gravity driven solution concentrations, the concentrations, so then slowly so reach this surface of the seed crystals like this. So already uh, we place a platform, or we provide the platform like a seed crystals. So then these concentrations what we have achieved at the top of the solutions, by means of gravity driven concentration concept, these concentrations so reaches this surface of the seed crystals. That is seed crystals that reaches. So then it forms a two-dimensional nucleation, layer type nucleations. Then so when progressively we can follow this type of ones, so we can grow a bulk single crystals. You see that, so every day we can watch how much of the solutions evaporated. Then you can add some amount of saturated solution from the top. By means of adding these solutions, by means of adding some solutions, we can avoid this type of microbial growth in this unidirectional technique. So this is the one of the important technique. So we can avoid the microbial growth by slightly disturbing the solution daily, or we can add the solutions so in the from the top of the vessels. Then you see that suppose all the solute crystallizes in this vessel. So even so you can add more number of solute day by day uh, by means of adding the saturated solution. So using the ink puller or some other vessels, so you can add some amount of it may be 2 ml, 3 ml or 4 ml only. So you are going to add every day. So that gives the uh, good quality single crystals. So we can grow a bulk single crystal as well as the 100% of the solute we can convert into the crystals in this technique. So following this technique, there are n number of investigators involved in the growth of bulk single crystal by this technique, unidirectional technique. Myself, Dr. Sethuraman et al., we used this type of vessels to grow a ADP single crystals, and then Justin Raj et al., in order to provide the heat to the vessel, so they use the bulbs. So instead of using the heaters, they use the bulbs. So, and then in order to avoid the Dinagaran et al., in order to avoid the multinucleations, so usually during the crystal growth, the multinucleation happen at the top of the vessels that settled at that crystal surface only. So therefore, in order to avoid, they use the bent type crucibles. So at the top one, so suppose multinucleation happens, that may settle at this side, so then we can grow a good quality single crystals. This is the one type of modifications they made. So far I have given some methodology to grow a single crystals, some basics of applications. Now I'm going to discuss about the materials point of view. So for our research, we have taken the semi-organic materials. Semi-organic material is a new class of materials. From these materials, we can get um, advantages of organic applications as well as the inorganic advantages. So therefore, this type of combination of organic and inorganic compounds that leads to the new class of material that is called a new semi-organic material. Example I can give, L-arginine is the organic one, hydrochloric acid is the inorganic, strong inorganic one. When you mix these two, that leads to L-arginine hydrochloride. Most of the semi-organic formations, semi-organic single crystal growth formations, we can use the amino acid materials because that crystallizes in non-centrosymmetric crystal structures. This non-centrosymmetric crystal structures more favorable to exhibits the second harmonic generations properties. So therefore, many of the investigators, they involved to synthesize the very many materials using the amino acid based semi-organic materials. Like you see that the combination of this amino acid and inorganic acid salts, that gives the actually the thousand number of materials developed, very many thousand number of materials developed using the amino acid based materials. Like L-arginine phosphate, L-arginine monohydrochloride, L-histidine nitrate. Here I have listed only few only. So for our case, we have taken the L-arginine and the L-lysine amino acid based material to grow as a bulk single crystals. Before to grow as a bulk single crystal by this unidirectional method, we perform some literature survey on this one. You see that already there are n number of why we have chosen this L-arginine monohydrochloride, monohydrate, and monohydrobromide and monohydrate means LaHCl and LaHPr. This is the structure of that one, molecular structure of this LaHCl and LaHPr. So these materials that has the very many advantages, like it comes under the category of semi-organic, also shows the permanent dipole moment, and then it also exhibits crystallizes in non-centrosymmetric crystal structure. It also exhibits the birefringent property, piezoelectric, electro-optic, second harmonic generation properties. So we made some literature on this LaHCl, L-arginine hydrobromide, hydrochloride, these two materials. We found there are very many literatures available. Even you see this material is crystallizes in 1966 and 70 respectively. So Azal et al., he studied very many properties of this LaHCl materials. So then you see that even though they have studied different properties of these materials, the grown single crystals is very few millimeter size one. For device applications, we need 1 centimeter size crystal, 1 centimeter square single crystals. So therefore, we thought to grow a bulk single crystals of this material by unidirectional single crystals. With this literature survey, so we take that challenge to grow this material as a bulk single crystals by this technique. So this is the conventionally grown single crystals. We adopted this slow solvent method to grow a seed crystal of this LaHPr and LaHCl. Initially, LaHCl, to prepare the conventional solution, we used a commercially available LaHCl. LaHPr, we synthesized using the L-arginine and the HPr acid in 1:2 molar ratio. So this is the method, that is slow solvent evaporation method, adapted to grow a seed crystals of this one LaHCl. So water used as a solvent. This is the dimension of LaHCl, single crystals grown by slow solvent evaporation technique. So LaHPr single crystal, this is the dimension, this is the grown single crystals, conventionally grown single crystals. You see, from this one, we identify a direction to grow as a bulk single crystals. This is used as a seed crystals to grow a bulk single crystals, both these crystals. So for our case, we use the ample design like this. So see, this consists of two bottom portion as well as the top portions. This bottom portion we placed inside the constant temperature bar. You see, the top portions we maintain the different temperature environment. So by varying the temperature top and bottoms, we achieve the, or we increase the concentration of the solutions, we achieve the supersaturations. By means of achieving the supersaturation, we grow as single crystals of this material LaHPr using the unidirectional solution growth technique. This is the seed crystals which we use to grow a bulk single crystals of LaHCl unidirectional method. So even you see that in this unidirectional method, so we can choose that proper direction 001 directions, and the nucleation temperature is 23 degrees centigrade. Growth rate we can measure using this technique 2 mm per day. So we can also increase the growth rate, but we need to optimize the growth rate. So by trial and error technique. Yes. So this is the dimension of the grown single crystals. This one is the grown single crystals, unidirectionally grown single crystals of this one. LaHPr, this is 1 mm per day growth rate. This is the grown single crystals of LaHPr. So after the growth, we examined this LaHCl and LaHPr by means of high resolution XRD. So from which we have understand our conventionally, our unidirectionally grown single crystals that shows the low FWHM, the main peak that shows the low FWHM compared to conventionally grown single crystals. This is the 17 arc seconds. This is the 50 arc seconds. Suppose low FWHM means that shows the high quality. So our grown crystals also contains the very low angle grain boundaries. This may, so we can eliminate by controlling the temperature during the growth. Okay. So in this way, we have also developed two different crystals, or grown two different crystals based on the L-lysine based amino acid 1, that is LLDN and then LLDP, two materials. So this is the literature survey we made. So from which we have understand there are L-lysine based material that also shows the SHG, second harmonic generation properties. Okay. Okay, so this type of materials, L-lysine based materials, formed as a mixed solvents by Srinivasan et al. In 2001. So after the literature survey, after these publications, there are many number of mixed salts developed by Petrosian et al. Almost 30 new mixed salts developed by different type of amino acids. So initially, in order to synthesize our material LLDN and LLDP, so we first follow the synthesis procedure of L-lysine monohydrochloride. So in order to prepare the LLDN, so this is the reaction mechanisms we followed. L-lysine monohydrochloride and nitric acid, we have taken 2:1 ratio. So because of the protonation of this hydrogen, so we have get that reaction mechanisms. So finally, we can end up with this LLDN materials. This is the chemical formula of this LLDN. This is the L-lysinium, lysinium 2 plus dichloride nitride, LLDN materials. So after the preliminary investigation on these synthesized materials, we like XRD, FTIR, and thermal properties, we subject this one to grow as a bulk single crystals. This is the conventionally grown LLDN materials. You see that has the definite morphology and then shapes. So using this one, we identify the specific direction to grow as a bulk single crystals for nonlinear optical applications. So this is the slow cooling technique we employ to grow a single crystals of this seed crystals. So it takes 20 to 25 days. So this is the morphology of the grown single crystals, from which we have identified the specific directions to grow a bulk single crystals. The same that is the crucibles we used. This is the grown single crystals of LLDN, and then cut and polished piece of LLDN single crystals. This is the dimensions. You see 20 mm in diameter, 70 mm in the length. Growth rate is 1 mm per day. So we have also examined our grown single crystals and compared the data using the conventionally grown single crystals. This unidirectional grown single crystals that shows the high quality and then high transmittance. So this gives the idea about, so in unidirectionally grown single crystals, the systematic packing of atoms exist, so that decreases the lattice defects. So by decreasing the lattice defects, so we can obtain the high transmittance from these materials. We can minimize the defect centers, so that improves the transmittance of that materials. Okay. Then LLDP also the same synthesis procedure followed. This is the grown conventionally grown single crystal. Using the conventionally grown single crystal, we grow we have grown that bulk single crystals of the LLDP materials. So this is the polished single crystals of unidirectionally grown LLDP material. The size is 20 mm dia and 50 mm in length. L-lysine monohydrochloride also we have grown. Sorry, sir. By slow evaporation method. This is the grown L-lysine monohydrochloride single crystals. So the harvested ingot, then cut and polished wafer of this L-lysine monohydrochloride single crystals. So we have also chosen different directions of this L-lysine monohydrochloride. Okay, so to grow as a bulk single crystals. So with this, I would like to conclude my lecture. So in this lecture, I have given some idea about crystals and their applications. Then idea about the low temperature solution growth technique, like a slow evaporation and a slow cooling technique. So The materials point of view, semi-organic single crystals. So how we can form the semi-organic single crystals. So then using the unidirectional technique, how we can grow as a bulk single crystals. So that idea also I have discussed here. So with these small lectures, I would like to give some important information to the new researchers. So that is the budding researchers. Even you see that simple experimental experimental setups, we can develop a very good quality of single crystals. All these results, whatever the results I have presented here, so that is grown by two research scholars. They have taken 5 years of time. So each one they take 5 years of time. So this all this research published in international reputed journals. Okay, so we can, in a simple setup, we can grow a bulk single crystals. That one we can publish in a very good high quality, in fact, journals. That type of idea I would like to give here. With this, so I would like to conclude in this session. If you have any doubts or clarifications you need, please ask. Sir?
Over to the host.
Right, sir?
Yes, the host team will organize.
Yes, sir. Any doubts, please, audience? If you have any doubts, please, audience, please.
Let me thank you, sir.
Yes.
It seems that your incredible presentation inspired us a lot. Most of us were unaware of this area of research and information. We are amazed of presenting the subject in an interesting way. I personally want to thank you for sharing this knowledge with us. Incredible session again. Thank you again, sir.
Thank you once again. So I take this opportunity to thank the administration as well as the HOD of this department, all the faculties and principal of this college for this opportunity. Thank you, one and all the best.
Thank you.
Then, now the question and answer session is open for the participants. Those who want to raise questions, kindly unmute the microphone and can proceed with it.
Sir, you have mentioned about that amino acid based crystals, no?
Yes, sir.
Whether this low temperature solution growth is mostly applicable to that one alone or some other materials also.
So this unidirectional method.
Yes, I am asking the unidirectional method.
So we can use any type of materials. For example, you see that ADP single crystals grown by myself and Sevaraman et al. So even many type of materials like inorganic, organic, as well as the semi-organic materials, we can grow by this technique. First, you need to understand the solubility data. Okay, that solubility data are very important one to grow single crystals by this unidirectional one. Sometimes So higher solubility means sometimes that leads to multinucleations. So very many times we need to change the solutions. Okay, so therefore we need to understand that point, sir. So we need, definitely we can grow organic single crystal as well as the inorganic one, and then semi-organic also.
Sure.
There are number of literatures available, sir. I think in this unidirectional technique or Sankarnarayan Ramsam method, so almost already published 250 articles published in international journals in the name of Sankarnarayan Ramsam method or unidirectional technique by different researchers. Any student? I think this is a very, very basic talk or lecture. So particularly for student community. So our budding researchers, research scholars, I have given to you only. So if you have any elementary doubts, please ask. Professor Rayat, sir. So you
Host team, any questions in the chat box? Host team, any questions in the chat box?
No, sir. No, sir. So you have also involved in crystal growth activities, sir?
Sir, there is no more questions in the chat box, sir.
Then if that's to be the case, you go for the next proceedings.
Yeah, sure, sir. Thank you. Thank you once again, sir, for your bestowed presence and sharing of knowledge with us.
Thank you. Thank you.
Thank you, sir.
Thank you. Thank you all for patient hearing. Thank you, sir. Thank you for the effort.
Here comes the end of the session 1. And it is the time to express gratitude to all of you present here. And now let me call upon Thomas Fernandez of 2nd PG Physics to deliver the word of thanks.
Good afternoon, everyone. Gratitude make sense of our part, brings peace for today, and create us a vision for tomorrow. It's my immense pleasure to deliver the vote of thanks for this event to all the dignitaries assembled here. First of all, I would like to thank our chief guest, Dr. Ramesh Babu, Associate Professor, Department of Physics, Bharatiyar University, Tiruchirappalli. Sir, you provided more basic ideas about crystal and crystal growth. From the earlier applications till the present one, you gave many inventional ideas to us about crystal growth, and it will surely help us to make more and more innovation creations related to crystal. First of all, I would like to thank our chief guest, Dr. T.S. Shabi, scientist. On behalf of everyone present here, I extended my sincere gratitude towards you, sir. Next, I would like to thank our principal, St. Jude's College, Thoothoor, Dr. Anlet, an eminent personality who leads us and influences us in all the way of success. On behalf of everyone present in this webinar, I extend my gratitude towards you, ma'am. Next, I would like to thank Dr. S.L. Royer, HOD, PG and Research, Department of Physics, acting as the backbone of PG and Research Department of Physics, St. Jude's College, Thoothoor, and he is the person who provides an opportunity for our PG students to be a part of this webinar. On behalf of everyone present here, I extend my gratitude towards you, sir. Next, I would like to thank Dr. T. Shajini Rose, Assistant Professor of PG Department of Physics, St. Jude's College, Thoothoor, who took various steps to make this webinar in a good manner. On behalf of everyone present here, I extended my gratitude towards you, ma'am. Next, I would like to thank all our organizing members of this webinar who provide better support and encouragement in each and every activities. A special thanks to Dr. Ajin Sundar and Dr. Jenna making a proper arrangement in this webinar. On behalf of everyone present here, I extend my gratitude towards you all. Last but not least, I would like to express my gratitude to all the esteemed participants. This webinar will surely provide you a better encouragement and improvement to your scientific knowledge. And to the people who make this webinar a great success, on behalf of everyone present here, I extend my gratitude towards you all. Once again, I thank you all for your better cooperation. Thank you.
Thank you, Thomas. Dear all, thank you so much for your kind cooperation. Let's go for a lunch break. The next session will start at 2 p.m. I request everyone to join Google Meet on time. Thank you. Thanks again.
Abru. Abru. என்ன காட்சிட்டு இருக்க அப்ரு இன்னத்துக்கு வாயில வச்சிருக்கு சாப்பிடு குட்டு சாப்பிடு குட்டு சாப்பிடு குட்டு சாப்பிடு குட்டு சாப்பிடு குட்டு சாப்பிடு குட்டு சாயங்காலம் முடிச்சிட்டு சாயங்காலம் ஒன்னும் இந்த லோ லெவல்ல உள்ள பிள்ளைகள் போலயாக்கு இங்க இருக்குது ஒரு ஸ்டாண்டர்டா இல்ல ஒரு ஸ்டாண்டர்டா இல்ல கொஞ்சம் ஒரு ட்ரைனிங் கொடுக்கணும் மதியம் சாப்பாடு எப்படி என்ன கேப்பு ஏடிஎம்ல போய் எடுக்கிறேன். நல்லா இருக்கீங்களா? இப்ப இந்த ட்ரெயின் உண்டா?
ஒரு 12:30
அப்படியா? டெய்லி வர்றீங்களா?
வாக்கிங் கனெக்ட் மட்டும் வரும்.
அப்படியா? சரி
பேர்ல
சரி. ரொம்ப குறைவுன்னு கேள்விப்பட்டேன். ஏன் அப்படி? எல்லா இடமும் அப்படி
இங்க ரொம்ப மாசம் இங்க ரொம்ப மாசம்
7 என்னமோ சொன்னாங்க.
பிஜி ஃபுல்லாப்பா இருந்தாலும் பிஜியே 17
17 வந்திருக்க பரவாயில்லையே. அங்க பிஜி வந்து 6 தானே.
எப்பவும் ஃபுல்லா இருக்கும்.
அவ்வளவுதான் இப்பதான் இருக்கு. அதாவது சார் எல்லாம் இப்போ வந்து அங்க என்ஜினியரிங் ட்ரெண்ட்ல போயிட்டு இருக்கு. ஓகே ஓகே, அந்த மாதிரி போக ஆரம்பிக்கிறாங்க. இது ஒரு 2 வருஷம் அப்படி போகும் சார். பழையபடிங்க வரும் பத்து. அது இது ஒரு ரொட்டேஷன் இருக்கு. நல்லா ஹெல்த்தியா இருக்கீங்கல்ல சார்? இப்போ மேபி அரௌண்ட் 68 இல்லையா? 69 ஆயிடுச்சு. நல்லா ஹெல்த்தியா இருக்கீங்கல்ல? வாங்க, என்ன பார்த்ததுல ரொம்ப சந்தோஷம். ஓகே சார், இதான் எனக்கு வீடு
தெரியும்.
வீணா சொல்லி நான் இப்ப அங்கே தூத்துருக்கு கிளம்பிட்டு இருக்கேன். ஒரு செமினார் நடத்திட்டு இருக்கிறேன், வெபினார். ஆமா, அது ஒண்ணு என்னன்னு சொல்லி பார்க்கலான்னு போயிட்டு பார்ப்போம் சார். தேங்க்யூ.